Yeah? Yes. All right. Okay, so let's recall where we were last time. So we're looking at 4-point functions. And they have a so-called conformal block decomposition. Primary, not the identity, lambda 5 I k squared g delta k. Okay, that's it bar. So this is one decomposition, but let's stick to this for now. And of course, let me briefly remind you of these z bar variables. So we put operator 1 here, operator 3 here. We are in some z bar complex plane. Operator 4, we send it to infinity. And operator 2 sits then wherever it sits and has coordinates z, has a complex position z. So this was the picture. So that picture is just also to remind you that what the different limits are. So z2 0 is the 1, 2 OPE limit. Z2 1 is the 2, 3 OPE limit. And these blocks, well, I've given you various ways of writing them. Another way to write them is to say that you can write them as an infinite sum, z to the delta minus L over 2, z bar to the delta plus L over 2. And then, let me make it a bit smaller so it fits. Z to the delta minus L over 2, z bar to the delta plus L over 2. An infinite sum over n, m, going from 0 to infinity, c n m, z to the n, z bar to the m, plus z bar symmetrized. So this would be one way to write blocks, and it's kind of nice because you just see that the z20 expansion is, or yeah, the z to 0 or z bar to 0 expansion is very, very easy. It's basically an analytic function up to a simple power. So okay, this is the setup. One maybe dumb question, but I want to. Sometimes this causes confusion to some people. I don't think it's really necessary, but if you're given a function. So suppose some very powerful person gave you a 4-point function. How do you decompose it in conformal blocks? So what's the trick? What do you do? Someone gives you a function of z and z bar. How do you find the block decomposition of the function? It's simple, right? Sorry? This is the conformal block decomposition of this 4-point function. So suppose someone gives you a 4-point function, let's say up to the prefactor, someone gives you a function of little, that I denote little g of z and z bar. How do you find its conformal block decomposition? So let me do a toy question, toy example. So let's do a one-dimensional function. So let me say g of z is something like z to the p, 1 minus z to the minus q, for simplicity, and I want to decompose it into these one-dimensional functions that are building blocks for proper higher dimensional blocks. So I'm going to write Cn, and then I use these k functions, which depend on some number h, which can depend on n of z. Where these k functions where z to the h, and then these two have one hypergeometric, and let me just write it out what the hypergeometric function really is. Z to the n, where a, this Pochhammer symbol is gamma a plus n over gamma a. You see it's a polynomials for an integer. Right, so I want to know what the hn and the cn are for this particular function. So what do I do?
Just expand around some limit.
Around which limit? So, right. What's the leading, what's the first, what's h0? P, very good. Right, it's z to the p because that's the z to 0 limit of this function. So these things are all simple in the z to 0 limit. So h0 is p and c0 is 1. Right? And then you just work a little bit because at order z you will find that you'll have z minus z to the minus q. I mean, it's not entirely evident, so like entirely obvious because this is like 1 plus qz plus q times q plus 1 over 2 z squared plus dot dot dot. And this block itself, of course, this h of z is z to the h plus 8, well, times 1 plus hz over 2 plus h times h plus 1 squared over 4 times 2h plus 1 z squared plus dot dot dot. And so you see that at order z to the p plus 1, you're going to get the contribution from your leading block and from your leading block and from the series expansion. So for the next guy, you get h1 equals p plus 1, and you get its coefficient is, if I got it somewhere, q minus c1 is of course q, so that would take into account that, and then you have to subtract the contribution from your leading block, that would be a p over 2, so minus p over 2. Right, and now have matched the order z term and so on and so on. So if you want to do this, this is the game you play. This is how you decompose a given function into conformal blocks. Okay? So, I mean, a closed form expression for these C's is a bit hard. If I want 25 blocks, thing. If I want the first 2000, it's also, with a little bit of programming, it's easy to find. If I want a closed form expression for these coefficients, well, the dimensions are easy. It's z to the p plus n, but what are the associated coefficients? Well, it turns out that in this case, I think it's some 3f2 function, but you have to be a bit more clever on how to find coefficients. Let me erase this because it really fit inside the parentheses. So here's a claim. We want to solve these equations, so one silly thing you can try is to say, well, I'll start with a block that, well, sorry, I didn't write the crossing equations yet, but one silly thing you can try, so there's a similar, so the crossing equations, let me, similar expansion, but then that started around z equals 1. And so one thing you can try is I take a block and I just expand it in blocks in the other channel, and maybe then I can repeat things like that. Right? I take a block, I expand it in the other channel, I can go back to my first channel, I see what blocks I get, and so in this way I can try to build up a solution to the crossing equations. So that doesn't work so well, because the expansion of an S-channel block, what I call a block in this decomposition, does not decompose well in the other channel. That was a question?
I was just wondering why you added to, you didn't see one in the toy example because is it just
a C, sorry, I didn't need?
Why you added a C1?
Because I need infinitely many conformal blocks to, right?
Oh.
To decompose this function. Because this is not the same as just the 0 block. this block for the zeroth component is kp of z, which has a very complicated expansion, and that very complicated expansion is not this. It's a much more complicated beast. So I need a new one. I add one more. Well, then I have to match it up to order z to the p plus 1, up to, and so on. So there are of coefficients to be determined. The claim is that, to go back to this example where I look at the z to 1 limit of a single block, I need infinitely many blocks in this decomposition. This decomposition always requires infinitely many blocks. Again, if you have Virasoro blocks, a few of them, but a single Virasoro block decomposes into infinitely many things that I call conformal blocks here. So the proof is very simple, because as x1 goes to x3, x2 goes to x3. We're taking the z to 1 limit. What dominates there is what determines that behavior is the operator product expansion between 2 and 3. So, and the leading term, well, here you can see as z1 goes to z2, the leading term is just this 1, because these guys are all suppressed by these extra factors. So the leading term is just the identity in the OPE between 1 and 2. So as x2 goes to x3, it's the same thing. The identity in the 2-3 OPE dominates. So G, well, let me just write it for the full. For the full correlator. So in this particular limit, we have phi, 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 phi goes like 1 over x23 to the 2 delta phi, and then x14 to the 2 delta phi. That is the identity exchange, the identity contribution to the operator product expansion, the 2-3 operator product expansion. So what you'll find is that function g of zz bar as z goes to 1, let me write it like that, z goes to 1, behaves like, well, obviously, x12 squared, x34 squared over x13 squared, x24 squared to the power delta phi, which is z bar, this factor that we saw before, z bar 1 minus z bar to the power delta phi. Sorry, I don't want to write tildes yet, because that's a different thing. This is just like a limit. So this is what you need to reproduce in the z to 1 limit from this decomposition. Now this decomposition, of course, it stops converging exactly here. We discussed that. But at z to 1, right, it barely converges. And so the asymptotic behavior of this series must somehow reproduce this funny power. So what does a single block do? Well, a single block doesn't do that at all. As z goes to 1, it goes to something like log of 1 minus z, log of 1 minus z bar. And then there's subleading terms, with some coefficients that depend on delta and L that are not important. So if you want to reproduce this 1 over 1 minus z divergence, you are necessarily going to need infinitely many blocks. There's no way around it. The same is true in this simple example, which is another good reason to look at this example. So KH, so claim KH as z of z as z goes to 1 is like AH log 1 minus z plus BH plus subleading term. So even in this simple example, it's clear that from the z to 0 expansion that you can decompose this function into conformal blocks. And from the z to 1 behavior, here it blows up like a power. You see immediately that you're going to need infinitely many of these blocks. A single block will not do, or any finite combination will not do. Yeah.
When you say to decompose a function, you are supposing taking some assumption of the function you want to decompose?
Sorry? Any function? This is a claim on the case, and the case are just defined through a power series.
No, you are in the question.
In the question, I just picked one, yeah.
But how to decompose a function?
Right.
Can be any function that you can decompose?
Yeah, well, what do you need, right? So you see that I am just taking the series expansion around z to 0. And from that, I can try to decompose it sort of term by term. So as long as it's a function that's, say, has a good generalized power series expansion around z equals 0, with generalized power series, I mean not just integer powers, fractional powers, and it converges, say, for z between 0 and 1, then I have a good conformal block decomposition, yeah. Because then it's just basically a reshuffling of the generalized Taylor series expansion into blocks. Yeah.
Two questions. First, you need infinitely many blocks, but is there any way why there's, well, the coefficients in front of the blocks should decrease so that some, I mean, when you will look for these coefficients, you will have to find the leading terms. Is there any way that the theories of
Yeah, that's where I wanted to go next, actually, which is the asymptotic behavior of the coefficients, right?
Second question. Usually when you want to decompose something like the G of Z in your toy example, people, we have some orthogonality condition on the, for example, PH10 here. Do we have such properties so that you can just integrate G of Z times another function in order to find these coefficients?
Yes. But I'm not going to say how, because it's complicated. But this is definitely underlying a lot of the results that I am not going to talk about, but a lot of modern results in analytic understanding of this function relies on the existence of such an orthonormal set. Yeah. I'm not it's not quite that these are super nice and orthonormal, but they're related functions that are. So. So you need to reproduce this power from logs, and logs are weird. So but obviously, it would be nice to know, to use this idea a little bit more and say, well, what do these coefficients asymptotically have to be for very large dimensions so that I reproduce this power? What's the asymptotic behavior of lambda phi k as, say, delta k goes to infinity? Because it's this till, it's this infinite till that must be responsible somehow for transforming these logs into a power law divergence. So we know we have an answer to this question, and it's built on things called Tauberian theorems, which are mathematical theorems that you then have to work a bit to generalize to conformal blocks. So here are some mathematical theorems. And I think I'm not a mathematician, so I'm always scared of writing a theorem, but I think I'm doing it right. So if you have some power series with integer powers, in the limit as x goes to 1, it behaves like this. And now we're putting on our mathematician's hat, so we have to say what this tilde means. So this is the definition of the tilde here in these theorems. It's just that the limit of the ratio equals 1. Then these coefficients should somehow behave as if you were just expanding this thing, at least asymptotically. So let's expand this thing. This thing expanded is the sum n equals 0 to infinity, your generalized binomial coefficients. This happens to be the expansion of the right-hand side. And so indeed, it is true that asymptotically, up to factor a, these coefficients have the right behavior. For rho positive. So that this is the dominant term. Right. So this is the dominant term. So you can change a bit the low-lying coefficients, but the low-lying coefficient as x goes to 1 will just contribute a constant, and this is the dominant term. So to get this particular divergence, the asymptotic behavior of the coefficient must be this, in this precise sense as defined through the tilde. I'm not going to prove it. This one is actually on Wikipedia, if you Tauberian theorem, or more generally Tauberian theorems, then you'll find this behavior. So we don't have this. We don't have integer series. We have power laws, complicated powers. And in general, we have this z to the delta minus L, so it's more complicated, right? Yes? Yeah, it's Hardy, Littlewood, Tauberian. I think. So, of course, there should be some sense in which if you have now Cn x to the power hn, where h is some increasing function, hn is some increasing sequence of dimensions. If this happens, then what, right? What can we say about the coefficients? The c's are now, the powers of x are now more complicated. But you can still say something, so we should just rewrite this as an integral. So let me rewrite the left-hand side. 0 to infinity c tilde h x to the h dh. Let me write it in some this. For physicists, this is fine. So c tilde of h should just be a sum of delta functions, right? I can write it explicitly. C tilde h, just some sum of delta h minus hn. The coefficient Cn, sum over n equals 0 to infinity. I've not done anything. I've just rewritten this as a distribution. So then we can say nice things about the truncated version of this integral asymptotically. So let me do my sequence of boards correctly. So I started there. So I'm continuing on. No, I don't want to continue here. Sorry, because I want to keep that. The integral from 0 to big H of c tilde h dh does what it is supposed to do, which is h to infinity a over gamma rho plus 1 h to the rho. This is what it does. So to compare, let me add a little note, and since the board is getting crowded, let me add a little note in a slightly different color. This means that the partial sums of the Cn, right, you can just sum this up, and what this sums up to, if you're not too great with your gamma functions like me, then gamma rho plus 1. It's this. It's just a n to the rho over gamma rho plus 1. And so here you see the behavior, a h to the rho over gamma rho plus 1, but now in an integrated form. So, and if you want, let me say it in words. Let me write ... to remind you that if you're making notes, this is not the exact form of the theorem. There could be strange and stupid things happening, where these h's, the set of scaling dimensions, have some accumulation point or silly things like that. And then this function is just strange and who knows what. So you technically have to add that the function c tilde of h, or its integral, this guy, this as a function of capital H is bounded variation, which prevents these silly things from happening. But in quantum field theory, we don't expect that to be the case, this strange behavior. So if bounded variation does not, it means that this is certainly allowed, but these HNs should not behave too crazily. And if that's the case, then what I said is true. So this already is sort of good enough for a conformal field theory, right? Because if we just decompose the blocks, we forget that we're looking at blocks. We're just looking at power series in Z and Z bar. Let's pick Z real and Z bar to be also real, right? They're just the same real number. And this is just some generalized series expansion that we can plug in there, and then we just get a generalized series expansion of the function little g. That is basically this. And we know what it behaves in the Z to 1 limit, because that's just this thing, 1 minus Z. If you pick Z equals Z bar, it's 1 minus Z to the power minus 2 delta phi. So it's the same thing with rho equals 2 delta phi. And so the asymptotic behavior of the coefficients in the series expansion should be something like this. So this tells you a decent first thing about the convergence of the conformal block decomposition. But how the OPE coefficient, or the coefficients in the series expansion, must behave. So here there's a direct application to conformal field theory, but I'm not going to rewrite the same formulas again, where I'm just going to replace this x with a z and this rho with 2 delta phi. You can do that, right? You can see that it works. It does teach you something about conformal field theory. But of course, ideally, we would like a better result, because, I mean, this takes into account all these subleading CNM. Those are not so interesting for us. We would like to know what the OPE coefficients do. And if you define some OPE coefficients density, sum over n, lambda phi. So delta minus delta k. Let me see if I do this correctly. Let me, I think, yeah, I should have prepared this more carefully. Okay, so I'm gonna put theorem in. Let me try to fix this in the break. But roughly speaking, the idea is this: you define something like this. And now I'm summing over all spins, and I'm not sure if that's the correct way of doing things. But let's just take everything into account, all the blocks with all the spins. Then there is a result on the asymptotic behavior of this. So, and the behavior is that delta prime, d delta prime. So these conformal, these OP coefficients, as delta goes to infinity, again, just by dominance of the identity, what's that to, for delta phi minus 2. Something like this, up to a prefactor that I'm not writing. So the limit is of this thing is 1. And so the important thing to realize is that these OPE coefficients have an extra 4 to the minus delta in them. So they go to 0 very, very fast. Right? And so they go to 0 much faster. And it's basically because if you're taking into account a single OPE coefficient, it already takes into account infinitely many terms in the conformal block decomposition. Infinitely, one conformal block takes infinitely many terms in the series expansion into account. So you don't need the coefficients of the conformal blocks to grow as fast as the coefficient of the series expansion. And that helps you to get an extra suppression in these things. I forgot one more thing that is very important. Because there is a little caveat here, which is already at this stage. And it is that I should have said that these coefficients are positive or non-negative. And here also. Because if they're not positive, then you can have huge cancellations here on the left-hand side. These things can be huge and cancel each other so that you don't get anything in the x to 1 limit. But this result would no longer hold, because if these C ends very wildly, there's no need for them to have a limit. But the positivity of these coefficients guarantees that this is a theorem. And the same is true here. And of course, for conformal field theory, we have positivity. We have it definitely for the conformal blocks, and it turns out that these C and M are also non-negative. So it is nice. We're in good shape. Yes?
The last equation. Oh, we raise the second delta. It's P delta, which is the function, and the integral of P delta then is...
Yeah, I call it rho of delta. It's the integral that behaves like that. Yeah.
But P delta is a function of delta?
This rho is a function of, it's defined like so. And that's the guy I integrate. So it's the asymptotic behavior of rho of delta prime d delta prime. So think of it as a measure. Right? It's exactly analogous to this. No? Okay, any more questions? Yeah, so sorry, I think this is correct, but I'll check it in the break. What's exactly going on here? So these are the kind of games you can play with the crossing equations, or more generally with this conformal block decomposition. We understand a little bit the asymptotics. We understand a little bit how the coefficients either of the Z series expansion or of the conformal blocks behave asymptotically. But these are kind of integrated stuff, right? It's sort of the sum over all the blocks at very large delta. Maybe at fixed spin. So you could ask, can we say something even better and get more fine-grained information about the theory from these kind of expansions? So we expand around the wrong end, and then we try to learn something about the asymptotic behavior of the OPE data. And so there's a nice trick which goes under the name of light-cone bootstrap. Which is the following statement. So let me write again this function g, lambda phi phi k squared g delta k lk. Now I'm definitely taking off my mathematician's hat. Although there is a way to make this rigorous, but this is the non-rigorous, quick, and very dirty argument that I'm going to present. So we're going to look at the z to 1 limit, but for now we'll take z bar fixed. As I said, right, you don't need to take z bar to be the complex conjugate of z. It amounts to going basically to Lorentzian time. That's why this is called the light cone bootstrap. Because you can think of this plane, you can think of z as x plus iy, or let me call it z as x plus I tau, z bar as x minus I tau, and tau is my Euclidean time, and then I do a weak rotation to Lorentzian time. So this is Euclidean, and in Lorentzian signature it would be z equals x plus t, and z bar equals x minus t. And now I have two real independent variables. So if you think about where we started statistical mechanics because we were looking at the three-dimensional Ising model, for example, which is what we're going to look at later. So these were three Euclidean dimensions, and it was all in equilibrium. But that doesn't prevent me from doing the weak rotation in this three-dimensional quantum field theory and reinterpreting, say, the path that we started with as a 2 plus 1 dimensional quantum field theory. So this is not the same as non-equilibrium Ising model, that would be 3 plus 1, because it's like boiling water that evolves with time. That's definitely 3 plus 1. This is a 2 plus 1 dimensional quantum field theory. Sorry? Z bar, and yes, like so. So I do a weak rotation in tau, so that means that Z and Z bar are both real and but independent. They're not the same. So there's one overlapping slice, of course, where tau and t are 0, which is where the Euclidean and the Lorentzian domains intersect. Yeah, Z also is real and Z bar is real. So more precisely, I want it to be between 0 and 1, which is where this is nice and convergent and everything. You can see that it works right here. This is just some series expansion, and this clearly works if you take Z and Z bar real and independent. There's no problem. So what happens? Well, we have the identity in the other channel, which the dominant term is this 1 over 1 minus Z to the delta phi, and then there is Z bar over 1 minus Z bar to the delta phi. And I omitted, there was a Z to the delta phi here, and that's the only thing I dropped because I'm looking at the leading term as Z goes to 1. So one thing you can do is try to see how you can expand, how do you get this power with this particular function of Z bar from a bunch of conformal blocks. And the idea to get an idea of what can happen, it will expand both sides around Z bar equals 0. So on the left-hand side, I'm just going to blindly swap two different limits, and this is where mathematicians would start to cry if they're good mathematicians, because you definitely cannot do that, but I'm going to do it anyway. And there is a more vigorous argument, and the paper was out a couple months ago. That is, the original idea that I'm presenting is from 2012 and 2012, I think, or 2014, something like that. And now it's been made really rigorous. So the result is rigorous, but the derivation is not. So let's expand around Z bar equals 0. So then you get Z bar to the delta minus L over 2. And then this power series in Z, but so it's actually the second term that is important. Then this power series in Z, but I once told you that this is just K delta plus L over 2. Sorry, Z bar, yes, of Z. So this is actually the behavior. And then there are subleading terms. So this captures the entirety, and it should be delta K and LK, delta K and LK. So this sums up all the coefficients associated to the leading term. So call them the C0M. Those are all summed up. And they turn out to give you exactly this function K back. So this should, of course, still give that 1 over 1 minus Z to the 2 delta phi. And now, to leading order, we'll have Z bar to the delta phi. So what do we see? Well, we see that we are going to need an infinite sum, because this K's behave like a log, and the log here an infinite sum of these logs should reproduce 1 minus Z to the minus 2 delta phi. So in fact, it's basically the same as the example that I erased, which is 1 over 1 minus Z. I wrote 1 minus Z to the minus Q. Well, here Q is just 2 delta phi. So, and then you can use these type of Tauberian theorems, roughly speaking, to say what the asymptotic behavior is of these coefficients, such that you reproduce this power of 1 minus Z. But of course, there's also now the Z bar dependence, and that's what makes it different from what we did before. Because the Z bar dependence here is delta K minus LK, and here it is delta phi. Delta K minus LK over 2, and there's delta phi. Not only do we need an infinite sequence of blocks, but we need the twist of these, we need delta K. So the claim is there exists an infinite sequence of blocks with, or like more precisely, the 4-point function contains an infinite sequence of conformal blocks where delta K should go to LK plus 2 delta phi. And the lambda phi K squared should go to the decomposition of this 1 over 1 minus Z. So let me call this A hat of K, where A hat of K is just a decomposition of 1 minus Z bar. So where am I? This was board C, so then I'm here. Now I'm being a bit schematic because you can add a finite offset here. So let me do it like this. Let me not add an offset. Then this, of course, because these operator dimensions they can be anything. It's like Z to the HK. So here you should view this in some integrated form, right? So I should say the integral of some should give me the AK back. Should be the integral of the AK. So let me put this in quotes, and you should understand this in the way that I still have here. So it should be like, there should be an integrated version of this statement that you can write down. Okay. So we have learned quite a bit. We've learned an infinite amount of data. So we're going to look, it's natural to look at delta k minus lk. And then let me look at this as a function of L for a 4-point function phi 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 phi. So which conformal blocks have we learned about? Well, we have learned about an infinite sequence where delta minus L goes to 2 delta phi. I'll put 2 delta phi somewhere. And so I'm not sure what they do for finite L, but asymptotically, there must be something like this happening. So remember that there's a unitarity bound, so delta minus L is bigger than d minus 2. So there's definitely a lower bound. And again, so let me stress what I have not written yet, that it relies on these coefficients being positive. Right? Otherwise, there can be big cancellations. Yes.
Is it a discrete series of we have some dense region with L, which is not L cannot take an integer.
No, L is always an integer because it's really the spin of the operator that appears in the operator product expansion. And that's a good local operator, so it has a good spin. It has a finite number of Lorentz indices. It's not some crazy thing. I'm looking at scalars, so there are no half integer operators appearing in the operator product expansion of two scalars. But yeah, like you can go nuts and do the same for fermions, and yeah, or for Fermi scalar 4-point functions, you'll find roughly the same structure. So there's more. I'll use yellow, say, to give you results that I have not proved, but I still want to show. So this works, well, this never worked because it was not a rigorous theorem, but there is a version that works, also for the subleading powers in Z bar. So the Z bar series expansion will just give you integer powers of Z bar around Z bar equals 0. So it's delta phi plus an integer, which means delta minus L is 2 delta phi plus twice the same integer. And the lambdas do whatever they have to do. And so you will find the same result for 2 delta phi plus 2 and 2 delta phi plus 4. And so on. So this is the idea that this is the picture of the spectrum that we learn from this light cone argument. So now we're basically done, right? We've already solved the large spin behavior. So there are just a couple of low spin OP equals that we'd like to. Well, we're definitely not done. It's much more complicated. We still have an infinite sequence of blocks. One thing that's nice is that you can also try to see, well, this is the leading behavior as z goes to 1. There is to the delta that I killed, which gives you some power law corrections to this behavior. But there's also, there are infinitely many other conformal blocks. So the next block here will be, so there's an order z term that I did not wrote. But then there's also, well, let me do it like this. So there's a 1 plus order z term. And then there's the next conformal blocks in the sequence, which is order 1 minus z. This is the z to 1 limit. And then there is the next block. How does a block behave in the z to 1? A z to 1 block behave in the z to 1 limit? Well, it's, sorry, a block with its arguments are flipped with z going to 1 minus z, but we're looking at the same limit, so it's basically the same behavior, is what I want to say. It's 1 minus z to the delta minus L min, I want to write a min there, like the block with the lowest value of delta minus L in the 2-3 OPE, that gives you a power here, and that gives you a small correction to this. We'll find that these corrections here are dictated by the blocks that appear in the 2-3 OPE. So you really have that delta minus L is goes to 2 delta phi plus some block, the contribution from some block. So that will be some operator that I'm going to call K min. It's the coefficient of that block. There's some numbers. So some gamma functions and so on. Let me just write the number. And then it's important to realize that this is suppressed by the spin. So for large spin, this correction vanishes to the power delta minus L. So there are power laws. So, okay, this is all a bit vague, but roughly speaking, there are power law suppressions to this, power law suppressed corrections to this asymptotic behavior. These power law suppressed corrections can be calculated sort of block by block, and because they come from blocks in the other operator product expansion. And so we don't just understand the asymptotics, we also understand a few corrections to those. Provided, of course, you know what the blocks are in the other channel. And then finally, one thing you should, so we have say spin 4, spin 6, spin 8. For identical scalars, there are only even spins appearing. There's, of course, one operator that we know, which is the stress tensor. T mu nu, which sits there. So one thing we can do is to check that the roughly reproduce, check how well they work, these corrections. We can extrapolate these results. We plug in, we compute this, which is an asymptotic series, and we just plug in L equals 2, which is stupid, but because there are infinitely many powered suppressed corrections that we throw away. But you get a pretty good approximation. When you plug in L equals 2 and you plug in some data from the three-dimensional Ising, that I'll discuss next how we can obtain it, you get something like this here should be 1, and get 1 for up to 2 or 3 significant. So it's nice. Story here that this can be improved in many different ways that I'm not going to talk about. After the break, I wanted to talk instead about numerical approaches to the bootstrap. Are there any questions? Okay. Yeah? No? Yes, there's one. These A hat are defined so that let me say this. This is definition of the A hat. So these lambda 5k squared must behave in this, just like the A hats.
But the A hat, in the same spirit of the integral estimation.
Yeah. So it's really this, and yeah, there's an integrated version that we should define. But the integrated version of these lambda 5k squared, so it's the integrated version of the lambda 5k squared that should behave like the integrated version of the AK.
So it's the second theorem there.
Yeah, it's a version of the second theorem, yeah. Because we don't really know what the delta k's are, yeah.
Other questions? So then let's take a 10-minute break.
Our goal is to, well, okay, I'll just start and answer your question. All right, so let's start. So our goal, of course, is to determine, in particular, these critical exponents. We want to know what delta sigma and delta epsilon are for the three-dimensional easing model, in particular, or for any other conformal field theory that we have out there. And so what we have done so far is just analyze these equations a little bit, and we didn't quite get to the relevant scalar operators in the theory, right? We didn't get to the spin zero operators with small dimension. We discussed operators with very large scaling dimension or very large spin. And that's where we have control, but as it happens, we lose the control a little bit when we look at spin zero. And as someone else pointed out in the break, it's a difficult thing, right? These equations were written down in the 70s, but it took a long time for people to understand how to attack them. You have infinitely many equations, because for every point z and z bar, I have an equation that needs to be obeyed. So that sounds very powerful. But at the same time, you have infinitely many unknowns. You have an infinite set of lambdas and deltas. And that's just for a single 4-point function. And in principle, all the 4-point functions all the 4-point functions need to obey for any combination of the positions. They need to obey equations like this form. So here I wrote again the crossing equations, right? This function g that I introduced. If I take the operator product expansion in the 2-3 channel, and I compare it to the 1-2 channel, I should get the same function, and that statement is encoded here in these equations. And then I substitute the conformal block decomposition of the 1-2 channel and the 2-3 channel, and I subtract them a little bit. And I get basically this type of sum rule, where I just have the blocks, all the blocks that are not the identity but their coefficients, the difference between the 1-2 channel and the 2-3 channel contribution should give you, or if I subtract out the identity, it should give you this, the identity. So I guess there should be a relative minus sign. It should give you the identity and in the 1-2 and the identity in the 1-3, in the 2-3 decomposition. So these are the equations that we're going to look at, and these functions f are just complicated beasts. They're combinations of a conformal block and its block, the same block in the cross channel. So the trick here that was discovered in 2008 in a famous paper by Ratazzi, Rechkov, Tony, and Alessandro Vicky, was to forget about trying to solve these equations and instead try to see when you cannot solve them. So what would it take to prove that these equations cannot be solved? So the idea here is you're going to make some assumptions on the set of deltas and lambdas, or maybe you're going to make some assumptions on the lambdas, sorry, the deltas and the L's or the lambdas. Let's make some crazy assumption. And if you make a crazy assumption, you should not be able to solve these equations. So how do you prove that? And then what remains? What are the non-crazy assumptions? That's the picture that was sort of the paradigm shift that was necessary to understand how to attack these equations.
Where do those equations come from, the F equations?
This is...
Is that definition or are these formulas?
This is the statement of, this is nothing but a rewriting of what I wrote before. No?
Yeah, but now you use F instead of G.
Yeah, this is F. Definition.
Oh, you mean the definition is below and what you... Okay.
Yes. Yes. So we introduce... So how do you prove that something cannot exist? Well, the way we do this, there might be other ways, but this is how we do it. We're going to look at functionals, linear functionals. So linearity, we know what it means, and a functional is just it's something that eats a function and spits out a number. It's a map from functions to numbers. So we'll look in particular at, and it must be linear, so we can look at something. A typical way that you would write a functional would be something like, if it's a function of two variables, you just write, you introduce some kernel, and you integrate your function against some kernel over some domain, and that would be a good way to define a functional that is linear. Another way to define a functional would be to compute some derivatives of this same function and evaluate it at the point, let's say z equals z bar equals a half, which is a nice point because it's sort of halfway between the z and 1 minus z points, and both decompositions converge there, so this sum definitely converges there. And in fact, you can even take a linear combination of these things, because a linear combination of linear functionals is still a linear functional. So with some alpha mn that are just arbitrary coefficients, and we're going to take them real. So this is the tool. And what are we going to do with this? Well, suppose that you're looking at the 4-point function of a scalar operator, primary operator as always, whose dimension is delta phi. Let me first do something strange, and then I'll refine it a bit to get something that makes more sense. Suppose something crazy exists. Suppose there exists a functional that, and it acts on this f00, the identity contribution from both conformal block decompositions. It's positive. And suppose that it is negative, or at least non-positive, for all delta greater than delta star of L, where delta star, so for all the deltas that can appear in this sum. And remember, there are lower bounds on these deltas. Delta star, well, delta min of L. Where delta min of 0 is the lowest operator that can appear for spin 0, so that's d minus 2 over 2. And delta min for spin L is L plus d minus 2. Because that's the lowest operator that can appear in a reflection positive theory. So suppose you have found suppose such an alpha exists. Then obviously we have a problem, right? Is that clear? That should be super clear. Because I act with this alpha on both sides of this equation, a positive number on the right-hand side, and by linearity I get a non-negative number on the left-hand side. And non-negative numbers are not positive numbers. So if such a functional would exist, then there would not be any solution to this equation. A reflection positive TFT would not exist, or this delta phi would not be a consistent delta phi in any reflection positive CFT. So this is the crazy thing, right? This is such an alpha almost never exists, but
Why is it totally impossible?
how can it be possible? The lambdas are real numbers, so their squares in a reflection positive CFT. The lambdas are real numbers. If you can make them imaginary, yes. And right, I'm using reflection positivity in two ways. It's the non-negativity of these coefficients, and it's these unitarity bounds. Yeah. No, because, oh, there's an equal sign here. No way out. So then there would not be a reflection positive CFT with this delta phi. Well, that's not something that we can find. Such an alpha, I think I found 1 or 2 cases in Virasoro blocks, but it's very exceptional. So basically, such a thing does not exist. But what does exist are alphas where we make some assumptions on the spectrum. So we're going to say that this is some delta star, which is strictly bigger than d minus 2 over 2. So what does this tell you? Can we write something rigorous from this? Then we have a universal result for reflection positive CFTs, right? So every primary phi, every primary scalar of dimension delta phi must have something. There must be something in this conformal block decomposition to make this work. So in the conformal block decomposition or in its self-OPE, let me say it. So the OPE of phi with itself what must exist? What kind of block must we have in order to obey this equation? Does people see it? Did I write it incorrectly? I think I did it right. So we act with the functional. We get a positive number. We need to get something positive. We're never ever going to get something positive from all the operators with spin, nor from any operator whose dimension is larger than delta star, any scalar operator. The identity is out. The identity is not there because I moved it to the left. There must be a scalar with dimension less than delta star. So every primary scalar must have in itself OP another, well, a primary scalar with less than delta star in a reflection positive CFT. So that is the statement I can make. Why? I think this. Right? So this alpha. No, I changed the definition with blue. Delta min is just some number that I pick. And now it's delta star. Yeah, sorry. And it's strictly bigger than d minus 2 over 2, the unitarity bound. Right, so this alpha can look a bit like this. So for spin 0, for spin 2, for spin 4, and then now I'm out of space. So we start at d minus 2, L plus d minus 2, which, well, for spin 2, it is just d. And here it's d plus 2. We don't really care. We are in reflection positive theory, so we don't really care what happens below these bonds. Here we don't care. Alpha can act on these kind of conformal blocks, but they're never appearing. And so then this alpha must be, sorry, we don't care all the way up until d plus 2. So this alpha must be positive here, maybe 0. And then there's an identity operator here. Sorry, this is the scalar with dimension 0 d minus 2 over 2. The scalar with dimension 0 is the identity operator. So this alpha is positive on the identity operator. Oh, sorry, negative. Well, it's positive on the identity operator. I have a minus, so, okay. Yeah, I think I want it like this. Then it dips negative. It's positive. This is because I flipped my definition of the identity. This is annoying. Yeah, it's negative on the identity, but you see I have a wrong definition because the extrapolation of this to delta equals 0 is minus what I call f minus. I can fix it, but it's, shall I fix it? Yeah, so I'll add a minus sign here, I'll remove it here. Okay, and then I have to change this sign here. This. Now it's fixed, I think. Right? Because now we need to get something positive on the right-hand side still, because the minus signs cancel. And so now it's fixed. So we need to get something, well, in this case, I want to say we need, so.
Then isn't the second one supposed to be positive?
No, I think this is correct. I think this is correct.
You say that alpha of delta phi should be negative. So what are you plotting?
Alpha of f should be, sorry, yeah. No, you're, yeah, and so now I'm, right, I can flip everything. I could also have flipped it this way. This is the same. This is alpha sending alpha to minus alpha, and that's what I plot. Yeah. Sorry.
And the first one should be negative.
No, because now alpha is positive on f0, so I get a negative number on the left-hand side. But alpha on all these other guys is positive. So this would give such an alpha gives an obvious tension. Because here there's alpha on f00 is positive, so this is with a minus sign, so negative on the left-hand side. And this is, yes, thanks, sorry, I should have done this more carefully. So there's tension, because in this world here, what I plot here, it should be, I should get 0 from the contribution from the identity and then everything else. And I get something positive from the identity in this world, I get something positive from everything else, but in the end I should get 0, and the 0 can come only because there will be some operator there, which gives a negative contribution. Delta star, it should be, is it okay? Yeah, it's next to the 0. Yeah, yeah, this worked. I mean, in fact, I get something more, right? With this particular functional, it definitely shows that there has to be an operator. There has to be some contribution in the negative region. So there has to be an operator in this window. So the way I plotted this, you get a slightly better result than what I show, but what I show is definitely, what I wrote there is definitely also true. Okay, yeah.
Why is L always even?
Because these are identical operators, and remember there was the 1-2 crossing equation which introduced the -1 to L in the conformal blocks. And so only even conformal blocks can survive for identical operators. Identical operators are important because if I don't have identical four-point function of identical operators, well, the equations change a little bit, but in particular here you will not have a square. We will have phi1, phi2k, and phi3, phi4k. And that's not necessarily positive. So this is, in some sense, a slight modification of what's called a linear programming problem. You want to find, at least if your functional is finite dimensional. So if you have a finite dimensional space like this, suppose we truncate this up until some n. Now we have a finite set of numbers, and we need to find a finite set of numbers such that star is obeyed where star is this, which includes this constraint. Right? So you're searching around in a finite dimensional vector space to find a linear combination, alpha Mn, such that you get the required positivity constraints on a continuum of deltas for each L. So in the old days, what we did is just discretize. So we said, well, this is hard because a computer cannot work with the continuum, but we just pick a small grid of deltas, and here also, and here also, and then it's a discrete problem, and now we have a finite number of constraints, a finite number of degrees of freedom. This is something you can just give to the computer. And sometimes, of course, the computer would come up with a functional that was not quite positive. It would have a little dip in between the points that you picked, but that you can check afterwards. And then you say, oh, that's silly, so we just add a point, a couple points there, and then the computer pushes it up. And in the end, we believe that we have functionals that are positive everywhere, right? So you can discretize when you want the computer to find a linear combination, but once you have found the linear combination, you can check at every delta whether it's really positive. So this is a rigorous game you can play with the computer. And in one way to formulate it is that alpha gives you a certificate that there is no solution unless you have like an operator below delta, less than delta star. So it tells you when there is definitely no solution to crossing. Like if there's no, it doesn't tell you that there must exist a solution to crossing here because maybe there are other constraints. In particular, we looked only at the finite dimensional set of derivatives. But the finite dimensional set of derivatives can give us a constraint, and it tells you that if all the operators have dimension greater than delta star in the scalar sector, then no way, there's no solution. Yeah.
So do you speak with the delta star, and then you find such alphas, you find that this is the operator for the operator in this type of B, or because delta star is not fixed?
Delta star is not fixed, right? So yeah, so one thing you can do is, well, linear programming, there's a mathematical theory, there's a primal version and a dual version. And the nice thing is that the computer can tell you, you don't have to search forever. Like the computer either says, here's my certificate, or it says, no, such a certificate cannot exist, at least not with within the finite dimensional space that you have given me. And so the algorithm terminates. It says yes or no. And if it's no, then you say, my assumptions were too mild, so I increase delta star a little bit. And then the computer says yes, no, yes, no. So you do a binary search, and then you find the best delta star as a function of n. So we fix n, like the finite dimension of the vector space in which the functional can look. And then we find, right, so here we have delta star, we fix for a given value of delta. Computer says, I found a functional, so there's definitely no way you can solve crossing. And then you say, okay, good. Well, and then you lower delta star, and the computer says, here I cannot find a functional with the n that you gave me, so it's a maybe. It's not a yes, because I have a finite dimensional constraint space, and then you just do this binary search up until for fixed n, you find some optimal value, delta star. And then you repeat this game for a bunch of values of delta phi, and you get some plot like this. It looks a bit like this.
In this tricky, you explore only the region which the functionals are given by that, that combination of derivatives. What about, for example, the functionals with the integral?
What about?
The functionals given by the integral. So, how do you discretize that?
Yeah, no, there are now ways where people explore this. This works very well numerically. And if you write a kernel, then the problem with writing these kernels and playing other games is that you want the functional to be positive also, like for all L and all delta. So if you write a kernel, what sometimes happens is that the functional is positive for spin 2, asymptotically, negative for spin 4, positive for spin 6, negative for spin 8, and then you have to take infinite linear combination of those to ensure positivity for all spins at large delta. So it's not easy to come up with I mean, people have done this now, but it's work of the past few years where people look at these kernel functionals.
Here, what we wrote is that you are looking for a normal field. But to do this, you need to know at least one delta phi to be able to look for the other one. So
Yeah.
are you playing this game as identity, for example?
The identity is out, right? It's in F00. So there's a
But then you need to know at least one of the delta phi.
non-trivial primal scalar. Yeah, for every non-trivial. Yeah, we haven't solved it yet. We're not there yet. But if you have delta phi, then there must be a delta star. An operator with dimension less than delta star, sorry.
For example, if you're looking for a series like phi z, then you need to know at least one of the delta for at least one of the two fields to be able to know the one from the other field.
Yeah, with this game, yes. Yeah.
That's very important.
Yeah, so we have to improve our game. Right? But this is, it's not 11 yet. Right? So this is n, and then of course, if you give the computer a bigger vector space to search in, so you increase n, then you're going to get a better bound. So this would be for n1. With a bigger space, you're only going to get a better bound. You're never going to get a worse bound. So with a bigger n and 2, you get something like this. And then n3, you get something like that, and then you stop because you want to write a paper and you don't want to have infinite computational, like spend all your computational resources on one plot. So this is the game that people play. So you get these, you see these kind of curves sometimes where people plot different values of n, so the reader can sort of see how things behave with n. Yes?
Can you clarify how finding a bound on delta star is solving the problem?
It's not. Not yet. So this is what the plot looks like. In the original paper, it looks roughly speaking like this. So there's a unitarity bound d minus 2 over 2. So, which in d equals 4 is just 1. And if it's exactly d minus 2 over 2, then it's just a free scalar. And the operator product expansion of two free scalars contains the operator phi squared. So this would be on the horizontal, like the intersection point here. And the intersection point in this direction is just d minus 2. So here we understand it. This is just a free theory. And the bound happens to come very, very close to free field theory. Here we don't understand. Like, do you know of any four-dimensional conformal field theory with an operator of dimension 1,3? I don't, 1.3 approximately? I don't know. But if there exists such a conformal field theory, then in the OPE of this guy with itself, there must be a scalar with a dimension less than some delta star. I think for 1,3 it's like 3,8 or 3,9.
Do we have a theory of the convergence in N?
No. Open question. Very interesting open question. Experimentally, it's a power law. It's like 1 over n. Sorry, it's integer powers, 1 over n, roughly. We don't know why. Let's do d equals 3. So this is 1/2, this is 1. So people do the same in d equals 3. That took a lot more work because the 4D blocks were known. There were these hypergeometric functions in terms of the case. The 3D blocks were not known, so people had to work. But what you find is this magical curve that looks a bit like this. where there seems to be, experimentally speaking, some sharp kink in the plot. And if you see where it is, then of course, famously, this is about 0.518 something, and this is about 1.41 something, which are, roughly speaking, the right scaling dimensions for the three-dimensional critical easing model.
Do we know that this technique of looking for linear functional is, I don't know, the most clever way to some constraints on data? I know, I think one could think of something else, rather than just applying functional to both sides, but that's very specific.
Yeah, good luck. I don't know. This is what works. Yeah. No, it's an excellent question. I mean, but it's exactly the question you should be asking. Maybe the thing that I should have mentioned. But yeah, we don't know. This is just I'll tell you what works and what we're doing, and that this is a thing that we're throwing huge computer resources at, and we hire a software engineer to write a better version of the software that does this linear programming problems and its generalizations. Yeah. But I mean, we see it work, but if you have a faster way, then you can put this all out of business. Yeah.
Now we have found one scalar, and therefore we know it's lambda, right? So lambda 5 k the scalar, and so we can we do this iteratively? So we factor out the scalar and then look for another.
Yeah, you could. Yeah, but then you have to make an hypothesis on where this scalar is, and then you can say something about the next scalar. So then you say for every take a 4-point function of operator delta phi, look at an operator of delta, let me call it phi squared, because it's roughly that, and then you can say what happens after phi squared. So now you have a bound as a function of 2 parameters. So it's already more difficult to plot. You can just put that in a paper, but then you introduce a third parameter. Now you have a function on a 3-dimensional space, and that's difficult to plot. So that's why you don't see that in papers, but in principle, yes, this is a game that you could play.
We studied this as a function of the dimension. Which varies with dimension, including fraction.
Yes, that has definitely been done. And you get kink. I mean, the reason people were so interested in d equals 3 is that they also saw the same kink for 2D easing in d equals 2. And then later on, people did continuous d. But in non-integer d, there are some problems because technically the theory doesn't obey these reflection positivity rules. So it's true that these things are nice functions of d, and you can compute them in d equals 3.5, because it's always a function of 2 variables and otherwise analytic in d. So yes, it's computable. But it turns out that there are negative norm states, and therefore the coefficients are not positive. It basically has to do with sort of, what if you take, yeah, it's like you use the epsilon symbol, which is only defined in integer d. And then if you build operators with 2 epsilon symbols, they're parity even, but they can have negative norms in non-integer d. Okay, so we're almost there, and time is almost up. Where should I go? I'll just erase this. So sorry for all the sign mistakes. But I hope it didn't distract too much from the main conclusion. So this was nice, but then of course people worked hard and did all kinds of generalizations and further applications of this. Of this core idea of finding functionals. One thing you can do is you look at 2 operators. And we're getting so close to easing that I'm going to relabel them. So let's look at 2 operators. One is Z to even, one is Z to odd. And I'm going to call them sigma and epsilon. And what this Z2 symmetry says is that in the OPE of operator product expansion of sigma with itself, well, there must always be the identity. But then sigma itself does not reappear. So only epsilon can appear. And in epsilon, you get 1 plus epsilon plus dot dot dot. Epsilon, you get sigma plus dot dot dot. Now so this, roughly speaking, is a bit like the Ising field theory, the relevant scalar operators in the Ising field theory. But there's more we can say about the Ising field theory because we know something about dot dot dot. Because we believe very strongly that to get to the critical point, you only have to tune the temperature and the magnetic field. Those are the two relevant operators. So these dot dot dots means that scalars must all have bigger dimensions bigger than 3, bigger than or equal to 3. We're going to do numerics, so the equal sign doesn't really matter. And of course, there can be tensors with delta greater than d minus 2 plus L. Now here, this is the same. And here, in fact, it's also the same. So if there's a Z2 symmetry that flips the sign of sigma, here you're only going to get Z2 odd operators. But again, in this Z2 symmetry breaking sector, we only have to tune the magnetic field, only one relevant operator. So here also we believe the same constraint appears. And so now, what people did, in particular Simon Stuffin, David Poland, Philip Cross, is they said, well, let me do this functional game, not just with the single correlation functions, but let me take all the correlation functions of this sigma and epsilon field, because I know those two exist. So, of course, there are no correlation functions with an odd number of sigmas, because sigma is a Z2 odd guy. So these are the 3 correlation functions you can analyze. And I'll leave it as an exercise. So to find the constraints on alpha that will tell you that there is no solution to crossing symmetry or not. You have now 3 crossing equations, and therefore there are 3, you can act with derivatives on this, you can act with derivatives on that, and you can act with derivatives on that. And you have OPE coefficients that appear everywhere, all over the place. So what you'll find is that this is not just a linear programming problem, it turns out to be a semi-definite programming problem, in the sense that you're going to get positive semi-definite matrices. This is just a schematic form of the operator product expansion. So if I have sigma sitting at x, sigma sitting at y, then this is, by the operator product expansion, the sum of other operators, lambda, sigma, sigma k, okay. And instead of right at y, and I'm just dropping all the position dependence and everything, and even the lambdas. I'm just schematically saying that in this sum k, there sits the identity operator epsilon and that. And in this sum, because of the Z2 symmetry, the epsilon does not appear, the identity does not appear.
It's so much like TFT, topological field theory, where you have this kind of algebra and fusion processes between.
Sure, you can say, well, there's an associative algebra underlying all of this, but since I'm just this essence, and in topological field theory, you just have the essence. But here, there's, of course, much more going on. There's position dependence that's highly non-trivial.
Would you like to comment on the truncation on the blocks themselves?
On the?
Is functional acting on the capital?
No, we truncate the blocks because we have to compute the action of a functional on a block, and a block is a complicated function. So then we have to work hard to do this, right? These hypergeometrics functions or whatever they are in 3 dimensions. So it is true that we don't know the blocks. We are always working with finite number, finite precision. So the action of the functional on the block, well, we compute it up to some error. So there's a minuscule error that comes from that we don't know the blocks exactly. But again, right, don't declare that the function is not just non-negative functional, but bigger than 0.1 or so, or 0.05. And then mathematically it seems to work. Again, you can check this after the fact. The computer spits out these alphas, and then you see that alpha maybe is very close to 0 here. So you zoom in here, you compute the block with 100 extra digits of precision, and then you check if it's positive or negative. And generally, that people have done tons of these checks. It all seems to work. So how does this plot change? Well, already from the sigma, sigma, sigma 4-point function, so let me now call them delta sigma, delta epsilon. Since delta epsilon is the first operator, there's definitely, already from the sigma 4-point function, we're going to get this plot, right? Because that's part of the constraints that we have. But from the other correlation functions and with the assumption, in particular, that other relevant operators, we're getting, in fact, much more. We're getting up to a small domain, a huge excluded domain, and a very small maybe domain. So of course, let me check. So there's a box around here, which is like, sorry, I already started. Let me change the axis. I want to say 0, 0, and then there's the unitarity bound, which is 0.5, 0.5. And then there's an upper bound, which is 3, 3, which is where these guys could in principle live. They're relevant, and their dimensions are above the unitarity bound, so they're between 0.5 and 3. And what we get is, roughly speaking, this very small island, where we have a maybe, and everything else is no. And then, to be completely honest, there's also some big region whose shape I'm actually not entirely sure of what it does, but there's some big maybe region here as well. And now you get all hung up on this big maybe region. But the more interesting thing is this very small maybe region, because that's roughly speaking where we think that Ising lies. And so you can zoom in very close to this region, and you'll find that it is basically this. It looks a bit like this. And there's a definite no. This is with the best value of capital N that we have to date. And the allowed values are now lie in a very small interval. So here's delta sigma, here's delta epsilon. And this value, I think I copied it. Someone made a Wikipedia page with these things. So if you search for Ising critical exponents, you get this thing. Where did I put it? So the lower bound is 0.5181479, and the upper bound 0.5181499. Here there's a lower bound which is 1.412615, and this is 1.412635. So there's some uncertainty of 1 in the before last digit. And everything outside of it, except for this sort of big peninsula, this is definite no. So the only values compatible with crossing symmetry are the values in this small sliver. And so this means, in particular, if you go to critical exponents, you find immediate constraints on the scaling the critical exponents for three-dimensional easing, which, let me remind you that the specific heat diverged like t to the minus alpha, where alpha is 2 minus d over d minus delta epsilon. So this was in the first or second lecture where we discussed how these critical exponents by these scaling functions were related to the scaling dimensions of the operators. And this is now 0.11008 with an uncertainty of 1 actually in the last digit. And there are other critical exponents. So for example, the correlation function is supposed to be doing this. But here you recognize this is just a conformal field theory correlation function. So eta is basically just 2 delta sigma minus 1. So eta is 2 delta sigma minus 1. So this is 0.036298 now, with uncertainty of 2 in the last digit. So that's where people stop the computer. So this is how you get these critical exponents. Eta, so you get the scaling, therefore just all the critical exponents. So this represents sort of the state of the art for the three-dimensional easing. Determined from the conformal bootstrap. So there are tons of other things, and I'm a bit out of time, but people have worked on this, of course, have done tons of other generalizations. You can look at the ON model, where you look at the where phi becomes a vector operator, an n-component vector. Then you have some indices floating around in your crossing equation. You have a different looking crossing equations because you have to contract these indices in some ON invariant manner. You play the same game, you try to find a functional, and you find islands for the ON model. Same kind of determination of the critical exponents. There's people looked at fermions, people looked at correlation function of the stress tensor, just the form of stress tensors, and so on and so on. There are tons of generalization of this core idea. Yeah, you had a question first.
Yes, because what you presented is really focused on the scalar fields and not about, L larger than 0.
Right.
Do we have such, singular expression and bounds for, I'm not talking about scalar because, scalar is noise, but I mean, we can expect all the kind of primary fields which are not scalar.
Yeah. So people have done an analysis of the 4-point function of the stress tensor. And I know that you have a question. And of currents and other vector operators and so on. It becomes much more messy because there are indices to contract and so on. It's complicated. But I think one thing that will happen probably in the next few years is to include here one more bit of information that we have about the three-dimensional easing model, which is the stress tensor. Not just here, the fact that it must appear here, but also that we can analyze crossing equations with the stress tensor on one of the external legs, right? The 4-point functions involving 1, 2, 3, or 4 stress tensors. And we can analyze all that. It's a huge system. It's super complicated. It's just a lot of work. But then probably you may get even an order of magnitude more of precision. You had a question.
You said that it was an interesting open problem, how the linear program converges as you make your space larger. But so is there, because that is unsolved, but is there somehow a rigorous bound or rigorous result that says that this small region is not closed eventually?
No, that's a different question, and it's also interesting. Is the solution to, we believe that there exists, this is not just a maybe, we believe there's a yes in there. That's one point, that's the three-dimensional easing model. We cannot find it, and you can ask if there is, if this point is part of a smoother, a bigger region or not. Is the solution to crossing for 3D easing isolated or not? Also, we don't know. I think the answer is no if you look at all the 4-point functions in the entire theory, because there are many more operators. But if you just look at those 3, I'm not sure. Maybe there's this. Maybe you can deform it a bit, but I don't know how. You were first.
When you say you can't find it, this is because the numerical precision and the lack of time for the computer, or
Yeah, well, it's also because of the setup, right? We only have no's. We have definite no's. We never solve crossing. We just show that it cannot happen. What happens is a little bit is that these functionals, right? Because if you have an extremal functional, you're very close to, like you're zoomed in here. So the functional is maybe like just positive here, then it's negative. Then you have delta epsilon. It's also just, it's all very tense, right? So you're just at the boundary. But then you see the contribution from the identity is basically 0. The contribution from epsilon is basically 0. And the contribution from everything else is non-negative. But in the end, it should sum to 0. So how can that be? Well, it's probably because the contribution of everything else is also 0. Right? So the functional, and this is what happens. If you plot it, it looks a bit like this. You see the functional being almost 0. And then the solution is just precisely, you get 0 from this block, 0 from this block, 0 from this block. And so you can read off a bunch of scaling dimensions. You get an approximate solution of crossing. You don't quite get the OPE coefficients here, but with the number of scaling dimensions fixed, you get, roughly speaking, you get the linear problem for the OPE coefficients. And what you've effectively done is you've solved crossing at the level of these derivatives. You have a bunch of derivatives that you've taken, and those are like derivatives of the original crossing equation, and you've solved those truncated crossing equations. Not the infinite set, but you've approximately solved it. Yeah. So that's how we know, in fact, we have estimates for like a few hundred operators in 3D Ising. Maybe 100 or 200 operators, mostly operators with spin. And we see very nicely this converges to 2 delta phi at large spin, because we have data for spin 40 or so, up until spin 40.
Maybe a last question before the break.
Should we then give it to a student?
I just wanted to ask about this peninsula. I mean, I guess this is maybe the initial result of this whole paper, but I guess in theory you can extra.
Yeah, we should. Yeah.
It's killer, but it's just, I mean, here you also cheat a bit because I guess you know the value of the exponent, so you know that Ising should be there even before the calculation. So,
right.
So you know, completeness, people have like managed to keep this peninsula with more.
Yeah, I think it would be great to kill the peninsula just so that you would sleep better at night. But one thing to try to kill it. So from these 3 equations, you're not going to kill it. Like this is basically converged. There will be no quantitative change if you increase the number of derivatives with which you analyze this equation. But so you have to throw in new operators here. So which operators are you going to throw in? Well, that's what I said. The stress tensor is the only one that we really know exists, and we know its scaling dimensions. And then, so if that does not kill the peninsula, then we have a bit of a problem, and we have to make more assumptions. I have to say something about the irrelevant operators in the theory. So we say, well, let me look at this. Here's an operator. So let me say that there must, in Ising, also exist some irrelevant operator in this window. And then we can start playing with that window, and maybe include it, and then kill the peninsula. But now it becomes a battle of like, maybe less and less interesting, right? Because you're making more and more assumptions, and in the end, you want to kill something that you already know is not easy.
Okay, but I mean, we shouldn't allow more questions. Okay, fine.